It is a common misconception that all joint configurations for the same pose can be achieved through owning continuous nullspace motion. Take a 3-link robot as example. Indeed, you can continuously move in this nullspace, but reaching this configuration must have a reconfiguration of the end-effector pose. Hence, for a nullspace of the robot to achieve a certain pose, we can divide between continuous nullspace and flipped nullspace. We introduce an additional description of nullspace, swivel angle. Observing the configuration, the robot can have a vertical reference plane and a shoulder, elbow, wrist moving plane. The swivel angle is the angular difference between these two planes. To adequately express both nullspaces, we design an enhanced dexterity map data structure. The map stores the solution status S and the corresponding joint configuration Q. 3 indexes control the end-effector frame by position, direction, and rotation. 2 indexes controls the nullspace in sense of the nullspace swivel angle and the flip nullspace. We could see a panel for the prototype toolbox for EDM generation. Different indexes could control robot in different ways, like position, direction, and rotation. Changing the index on the left will deliver a different configuration on the right. The most important contribution here is that the nullspace configuration could be independently controlled with 2 indexes in a clear way. The panel itself is quite informative. For more information, the toolbox and the dataset is open source for your exploration. Furthermore, we conclude a helpful concept, continuous nullspace span, in short CNB. In configuration space, from one configuration, we do the continuous nullspace motion to get one CNB. Different points on the CNB suggest different swivel angle, but the flip solution is in a totally different point in the configuration space, and therefore they can get an independent CNB. We could see an example of KUKA and CNBs in configuration space. We can observe how 2 kinds of nullspaces influence the robot configuration. The basic idea of our algorithm is quite straightforward. Reproduce the map, sort index kappa, and augment the missing data. Of course, there are many implementation details. It can be seen in the open source toolbox. We could observe many interesting things of EDM. For instance, for specific direction and rotation and flip, we use the number of valid continuous nullspace configuration as a score in each position. We can therefore get a map. Repeat this process to each flip region, we could get the full information of EDM. It could be observed that in different flip regions, continuous nullspace performances are basically the same, but there are from time to time low performance area in specific flip regions due to the joint limit. Many existing maps could be deduced from EDM by doing simple mathematical operation on solution status, configuration, or Jacobian. We can even combine them together to get a comprehensive consideration of the performance. Consider a case for path planning for the fixed-base manipulator from frame T1 to T2. Different maps suggest different start and end configuration Q1 and Q2. 20 different start and end configurations are suggested from different maps. The path in between, generated by the RT, is then evaluated by path length, distance to joint limit, and manipulability. The path is also displayed real-time on the bottom left corner. Nullspace information used for planning is also visualized on bottom right. For most existing maps, the evaluation matrix is assigned for each position or each pose in the workspace. This planning scenario fixes the base and target. Therefore, the planner have only one single value for the nullspace information for both start and end. This is also the reason why it is having an awkward path during long-distance reconfigurations. We also test a map that considers the continuous nullspace information. We could see planners are trying to use the nullspace information by choosing a better start and end swivel angle. The performances are averagely better, but still, the flip region information is missing. The full information of EDM contains information of continuous nullspace and flip nullspace. The information for EDM allows us to strategically select configurations with better performance in the same flip region. In conclusion, this thesis contributes EDM, which is capable of considering both continuous nullspace and flip nullspace. We can integrate many current evaluation frameworks to our work to make a comprehensive consideration of performances in different flip regions.